So we're in chapter 3. There's a lot of material in chapter 3. We've covered a lot already. Last time we introduced the property enthalpy. Recall cap H or lowercase h. What was cap H? Just U plus PV by definition, lowercase u plus P script V or lowercase v. True? Why do we even introduce this property? Primarily for open system analysis when we have flow through control volumes. But you can also find that if you take a fluid that's trapped in a piston cylinder apparatus, so my system is the substance that's trapped in the piston cylinder apparatus, and it's a constant pressure right here. And it starts out as, let's say, a two-phase. That's even easier to think about, okay? Maybe it starts out with a lot of it in the liquid form and just a little bit is in the vapor form, okay? We apply some heat to it. So we add heat during a process. So we go from state 1 to state 2. And during that process, probably the piston has risen as the substance has expanded. True? All right. So that's my system. There's maybe a little less liquid down here, more vapor. All right. Let's apply the first law to this process. So we have, how does the change in the total energy, E2 minus E1, it's equal to how much heat is transferred in during the process from 1 to 2, minus any work done by the system, the fluid, the system identified by that dashed line that's trapped in the piston cylinder apparatus, any work that it does during the process 1 to 2. We expand the energy into total energy, the total energy into internal, changes in kinetic, and changes in potential energy. And now we go through and we say, is there any information about changes in kinetic energy? Or do you think that the bulk kinetic energy of the system initially is equal to 0, and at the final state it's equal to 0? Can we cross out these two terms? Are they equal to 0 for this problem? Yes. They are. How about change in potential energy? This one throws students for a loop. They say, isn't the center of gravity maybe moved a little bit? Negligible. Okay? It's the center of gravity of this mass system, the center of gravity of that mass system. It's negligible change. Got it? So, change in potential energy, negligible. But do you think there's a change in the internal energy? If I put a thermometer in here and I measure the temperature, and I put a thermometer in here and I measure the temperature, will they be the same temperature or will they be a different temperature? I'm going to pause here because I want everybody to answer that question, and I want you to answer that question on a sheet of paper, and I will walk around and look at your answers. First row and third row, I can see all of them. The other ones in the interior, it's going to be hard for me to look at. But what I want to know is whether or not the temperature at state 1 is equal to the temperature at state 2. And then once you get that one down, tell me, what about U2 versus U1? So here's a question number 1. T1, is it greater than T2? T1 equal to T2? T1 less than T2? Here's another question. Is U1 equal to, well, here, let's keep it in the same. Greater than U2? U1 equal to U2? U1 less than U2? Got it? True? Those are two good questions. And then the next thing, well, maybe I'll continue with the questions. Here, Q-U-E-S-T, question. Okay, Q-U-E-S-T, that's another question. Here's another question. Is Q1 to 2 less than 0? Q1 to 2 equal to 0? Or, I'm having a hard time writing. Q1 to 2 greater than 0. Then another question. Is work 1 to 2 less than 0? Work 1 to 2 greater than, equal to 0? Or work 1 to 2 greater than 0? I have 4 questions I want you to answer about this problem. Before I pause, does anybody, don't tell me the answer, but does anybody want to ask me a clarifying question? No.
Is this work that we're looking at in the equation, or?
It's our traditional sign convention that we had this equation where this Q is positive in and this work is positive out because of the negative sign right there. All right? Does that help?
The gas in the piston is the system?
That is the system. I put a dashed line enclosing it. It does not include the piston. It's only the fluid, which starts two-phase, ends two-phase.
Is it,
There is a flame right here, and it's pumping heat into it. Here's another question. Is the pressure at 1 less than the pressure at 2? The pressure at 1 equal to pressure at 2, or the pressure at 1 greater than the pressure at 2? I think that's enough questions. I will pause, walk around, and I want you to answer each one of these in your notes. I wish I had more time and let everybody, go look at everybody and talk through with everybody. I'm glad there was a lot of noise and chit-chatter. You should sit near people, and if I do more of this, then you can ask each other questions and that, right? It's a two-phase mixture. It starts a two-phase mixture. The amount of weight on top of that piston, did I say it changed, or the same amount of weight on top of the piston? It's the same amount of weight on top of the piston. This is really one of those difficult concepts for students. If I have a piston here and I don't change the amount of weight on the piston or the weight of the piston, it's the same. True? But I have some gas below it. True? But somehow I take that piston without changing its weight or mass or anything, and I'm not going to be able to do this very good, so I'll just give up on that. And I change the elevation of that piston, okay? I change it up here, all right? Same piston, same weight of the piston, same cross-sectional area of the piston. It slides freely in the cylinder. There's no friction. It slides freely in the cylinder. Maybe I still have some gas below it, true? But tell me, what is the pressure in the gas below it? Did the pressure change between this case 1 and case 2? Do a free body diagram of that piston and you will convince yourself it did not change. But focus, yes. When you have a piston like this, do this. You go with the pressure on the atmosphere above it, pushing down. You do the weight of the piston, the cross-sectional area of the piston, and all of that determines the pressure below the piston if the piston's not falling or rising. And we're doing equilibrium. The piston's stationary. So there's a balance. There's a pressure below pushing up, and it's equal to the pressure above pushing down plus the weight divided by the cross-sectional area of the piston. Free body diagram. You've got to do it yourself. True? But now that it's been explained, intuitively a lot of students will say, if the elevation of that piston changes, the pressure had to go up or down. Well, maybe there was an infinitesimal increase in the pressure to get it to move up, but if it's not accelerating up, it's stationary, that was a quasi-equilibrium process. The pressure was always dictated by the weight of the piston and the atmospheric pressure above it. Terrible professor says, I want to make a tough exam question for those poor students in Thermo 1 so I can really have fun grading it and fail them all. So what does he do? He adds a roof. And he adds a spring. As the spring compresses, there's an additional force pushing down on the piston, and the gas pressure now is a function of the elevation of the piston. True? Oh, they're a terrible, terrible, terrible instructor to do that, but yes, that happens often. No, not that we have terrible instructors, but that we have terrible questions. Okay, so this is a two-phase mixture, true? It starts two-phase, it ends two-phase. It's constant pressure process. So once I know that P2 is equal to P1, can T1 be anything but T2? The student's intuition says you put heat in the system. When you put heat in the system, the temperature goes up. That's what your intuition says. But that's why this whole chapter is so important. Constant pressure phase change, temperature doesn't change. The boiling point of water at 1 atm is 100 degrees C. No matter if I've got the pot full of water and it's just starting to boil, or if there's just a little bit of water left in the pot and almost all of it's boiled, it's still boiling at 100 degrees C at 1 atm. You want to put a pressure cooker on there with a little stop to increase the pressure at which it's boiling in the pot? Well, you just boosted the pressure. Maybe now it boils at 120 C. But as long as the pressure cooker lid's maintaining a constant pressure, if it's full of water, it's 120 C. If just a little bit of water vapor is there, it's still 120 C. I mean, two-phase. It has to be two-phase. As soon as you've heated it up now and it's all boiled, it's all in the vapor state, you can continue to pump heat in. And when you pump heat in, temperature goes up. But what does the average student's intuition tell them? If I put heat in, the temperature goes up. And this is one of those cases where I put heat in and the temperature stays the same. They call that latent, hidden heat versus sensible heat. Sensible makes sense because if I put a little heat in, the temperature goes up a little. Put a lot of heat in, temperature goes up a lot. Latent, hidden. Old terminology from the caloric theory, but there you go. It's hidden heat.
There's still liquid in there.
Oh yes, you have to know. As soon as it's, let's say state 3 is now superheated vapor. Right? The piston may have really had to move far up. The piston dictates the pressure didn't change, but now the temperature could really go up. A lot of people got this correct, that the internal energy had to go up because you're pushing in heat, true? And a lot of people got that one. I don't think anybody got that incorrect. And a lot of people got this correct. From the perspective of the system, it's expanding, pushing back the surroundings, which is the face of the piston. But now let's get back to why is the enthalpy of use for a constant pressure heating process just like this. So we go back to this equation, true, and we go back to this equation. What is my boundary work in this equation? Is it the integral P dV? Yes, it is. Constant pressure, can I pull that pressure outside, the integral P dV if it's constant pressure? Sure can. So the integral dV is simply going to be V2 minus V1, true? Is that the integral dV from 1 to 2? The final volume minus the initial volume? So at this point, I know I'm begging for some more space here. When I want to multiply the P times the V2, I'll put P2 V2. And when I want to multiply the P times the V1, because it's constant pressure, I'll put the P1 V1 because P1 is equal to P2. But when I multiply by V1, let's put the subscript P1. When I multiply by V2, let's put the subscript P2. Now I have this all in here, so it's Q1 to 2 minus P2 V2 plus P1 V1, true? See what I did with the work? I calculated the work, the boundary work. Grab this one and throw them to the other side, rewrite the equation. You'll have U2 plus P2 V2 minus U1 plus P1 V1 is equal to Q1 to 2. Did I do the algebra correctly? Thumbs up if I did the algebra correctly. What do we call this group of terms? Enthalpy. This one, enthalpy. So what we find for first law, Q1 to 2 is equal to H2 minus H1. it boosted the enthalpy. And so that's maybe a justification for the introduction of the property enthalpy, but when we get to open system analysis, we'll use it all the time. Okay? This is a closed system analysis problem. Next one, what about the heat of vaporization, HFG? I need a new slide for that. Insert new page. If I start the problem, go back here, and I have just saturated liquid in that piston cylinder apparatus, true? This is 100% saturated liquid, no vapor, but it's saturated liquid. If I put a little heat into it, a little bit of heat into it, right? That's my heat flame. What happens to it? It starts to change phase. So as I continue, the piston may have risen dramatically, and we go from saturated liquid to saturated vapor. Now at this point, if I continue after state, this is state 1, state 2. After state 2, if I continue to add more heat, it'll become superheated vapor, and even if the pressure stays constant, the temperature will now go up. But during this process, the temperature stayed the same. The pressure stayed the same. So now you ask yourself, how much heat did I have to pump in to go from state 1 to state 2? Well, it's the final enthalpy minus initial enthalpy, the mass times the H2 minus H1, the mass times the enthalpy of saturated vapor minus the enthalpy of saturated liquid. That difference in enthalpy on a mass basis is commonly called HFG. HFG is just H of G minus H of F. And it's called the heat of vaporization. Because a lot of times they say, well, I have the system is at 10 bar. How much heat is required? Heat transfer in, heat. How much heat is required per kilogram to turn the phase, to make it go from saturated liquid to saturated vapor? You just look up HFG at 10 bar for the water or steam. True? So that's the heat of vaporization. Notice that this enthalpy is the only one to have 3 columns. Everybody else, specific volume, 2. Saturated liquid, saturated vapor. Internal energy, saturated liquid, saturated vapor. Entropy, saturated liquid, saturated vapor. Only 2 columns. What's that third column? HFG. Heat of vaporization. It's just a nice parameter. All they did was take this number and subtract that number. Why did they waste paper and space by, if all I had to do is take H of G and subtract off H of F, was it really worth doing it and putting it in the extra column? Well, okay, some books do it, some books don't. I mean, why didn't they put a UFG in there? UFG. Third column, they could have taken use of G minus use of F. Very, very few books do, but they could. They could also put SFG, S of F minus S of G, but they don't. It's too many columns. But this column, they said, well, it's probably worth it because that's the heat of vaporization. All right. Now, talk about reference states. You have to start energy measurements from somewhere. When you're looking at steam, saturated water, where is our energy measurements from? Where energy measurements are from, right there. You can see the number 0. So they pegged energy content for steam to have saturated liquid at the triple point. Isn't this the triple point? The saturated liquid's internal energy is given a numeric value of 0, and they make the reference. They make all subsequent measurements of U and H, because everything's measured from there, like U2 minus U1. Its measurements are referenced from this starting point. H at the triple point is just a slightly above 0. But this is the datum point. That's the reference. That's the beginning. We want to talk about refrigerants. How many refrigerants? 4 refrigerants, where we get tables of them. Where do they start? Well, they picked that the enthalpy, H of F, the enthalpy of saturated liquid at a temperature of negative 40 degrees C is given the datum point of 0. Let's go look at it in some tables. So here is refrigerant 134A. Here's a temperature of negative 40. Come over to H of F, enthalpy, saturated liquid, and see it's 0. For energy measurements, not for volume measurements, not for entropy measurements, but for energy measurements, both U or H, they started at that point. Let's go to the ammonia table. Find negative 40. Notice, negative 40 is not the lowest temperature they put in the ammonia table. There's negative 50. True? That's even colder. But when they come over here, the energy is set as a benchmark at a datum point of 0 for the saturated liquid. Does that mean if you're colder and saturated liquid, you'll have a negative enthalpy? Yes, you will. The magnitude's not as important as the change between states. Somebody could say, well, fine, let's pick negative 80 degrees C as the benchmark. You could have. They picked negative 40. Why did they pick negative 40? It's a very cold temperature, so most refrigeration is above that temperature, but it also coincides with negative 40 F. It's the same hotness and coldness at that numeric value, either on the Fahrenheit scale or the Celsius scale. It's the same. Now, this is very difficult, but I want to try to give you a roadmap. If you have to determine properties for superheated steam, often they give you pressure and temperature. The information was in pressure blocks, true? But to check it, to make sure you're superheated, if they give you a pressure and temperature, either find the saturation pressure for the given temperature and make sure that your pressure is less than that. Otherwise, you're not in the superheated region. Check to make sure you're superheated. Maybe this one's more logical. Find the pressure. Sorry, I got a typo right there. For the given pressure, find its corresponding saturation temperature, and then check that your physical temperature is greater than, or the input temperature is greater than the saturation temperature. Otherwise, you're not superheated. If you're superheated, this will be true. Make sure to get rid of that typo. Either one will check and help you determine if you're superheated. If you're in a two-phase region, if they give you temperature and pressure, well, then check by saying, give me the saturation pressure and see if it's equal to the actual pressure they gave. If it's not, I'm not in a two-phase region. Likewise for the temperature. Often, they may give you something like pressure and specific volume. What you do is, for that pressure the given, get V sub F, the saturated liquid specific volume, then get V sub G for the saturated vapor specific volume, and see if the specific volume they gave you falls in between. If it does, good, you're in a two-phase region. If it doesn't, you're not in the two-phase region. If your V greater than V sub G, guess what? You're superheated. Same here. Temperature and internal energy. Check to see if U is between U sub F and U sub G. And pressure and internal energy, and the list could be made a lot longer. But typically you're given pressure or temperature and another property. How about if you're subcooled or compressed liquid? Well, just the opposite of this. This makes sense for compressed liquid. The pressure is greater than Psat at the given temperature. This makes sense for subcooled. The physical temperature is less than the saturation temperature for the given pressure. I'm not saying these are easy. I'm just saying try to get the roadmap in your mind, because you'll have to go down this roadmap all the time. Thermo 1 for the rest of the semester and Thermo 2. So also you can look at these other properties to compare, but let's do this. Often you can tell if it's superheated, make your list of properties. Always kind of make your list of properties. A lot of times it's common to have pressure and temperature as the inputs. A lot of times pressure, volume, pressure something else, or temperature something else. But very common to have these as your inputs, pressure and temperature. When it's two-phase, you cannot be given T or P. You have to be given one or the other because they're not independent in the two-phase region. And then the new property kicks up. What is that new property, X? Quality. Is the quality in the list of good properties for superheated steam? Did I forget to put it there? It doesn't exist. How many times will I have a quality calculated by the student? It'll be the quality is equal to 1.13. Oh yeah, it's superheated. Well, yeah, you may have used that to determine it's superheated, but it is not. Don't use the two-phase properties, saturated liquid, saturated vapor, try to interpolate in between with a fraction, the interpolation fraction of 113%, and think you're going to get a lot of partial credit. Okay? The quality is only between 0 and 1. This is tough when you're first exposed to it. I'm trying to show you the common errors I see on exams. Don't want to see them in this class. So this quality exists, and so a lot of times you're given pressure and quality, temperature and quality, or pressure and something like volume, and we'll talk about how you turn that volume into a quality. Let's talk about this now. So you make in your mind a temperature specific volume diagram, and a line of constant pressure is constant temperature through the dome, saturated liquid, saturated vapor. There's my value, my numeric value for V sub F, my numeric value for V sub G, true? The quality is a measure of the fraction in between. So if I'm sitting right about midpoint, quality's half. If I'm sitting right in here, the quality is maybe 10%. If I'm sitting over here, the quality X is nearly 90, 95%, something like that. What was the definition of quality again? Quality was the mass that's in the vapor state divided by the mass liquid plus the mass vapor in my two-phase mixture. Let me kind of forget this right in here. I'll come back to it. If I have of total volume, I'll have the volume occupied by the liquid plus the volume occupied by the vapor. So here I have a container. There's the liquid down there, and here's the vapor up here. True? Do you see what I'm doing? I start this equation, and I have the total volumes made up of the volume that's occupied by the saturated liquid or the volume occupied by the saturated vapor. I then take this equation and I divide by M. What is the definition of volume per unit mass? So the specific volume of my mixture, having some liquid, some vapor, is the total volume divided by the mass, the total mass in the mixture. So that's equal to mass of liquid plus mass of vapor, mass liquid plus mass of vapor. Did I do that right? The total mass is the sum of mass liquid, mass vapor. If I multiply the volume liquid by mass liquid plus mass vapor, if I multiply by the mass liquid divided by the mass liquid, did I change that first term, volume vapor, mass liquid plus mass vapor, multiplied by mass vapor divided by mass vapor? You see what I'm doing? I'm multiplying by 1 the ratio of mass liquid over mass liquid, or mass vapor over mass vapor. So now, switch the order. Put this one there, and these over here. Put that one there, and these over there. And so I'll have the specific volume of my mixture is equal to the volume of the liquid divided by the mass of the liquid divided by mass liquid plus mass vapor, plus volume of the vapor divided by mass of the vapor, mass vapor divided by mass liquid plus mass vapor. Do all those steps make sense? And guess what this one is? Specific volume of my saturated liquid. We have a symbol for that, V sub F. What is this one equal to? The specific volume of my saturated vapor, which is V sub G as a symbol. What is this one equal to? Mass of vapor divided by the total mass. quality. And now the hard one, 1 minus quality. So if you're 90% quality, that means 90% by mass is vapor. You're 10% by mass liquid. That's all you're doing. You can rewrite this. V is equal to V sub F plus quality times V, plus quality times V sub G minus V sub F. So I could say quality is equal to the actual mixture specific volume, subtract the saturated liquid divided by the saturated vapor minus saturated liquid. That other page is saved if we need to go back to it. Now I'm just going to erase all of this. And what I want to do is I want to kind of give you a quick running order because you have to use this all the time, this type of thing. So a lot of times you're coming in with you're coming in with temperature and quality, true? So tell me, if I want to get pressure, knowing temperature and quality, how do I do that?
Temperature table.
All it is, Psat for that temperature. Well, how did you use the quality in this case? The quality just confirmed that it's in the two-phase region. Once I confirmed it's in the two-phase region, if you want the pressure, I'll give you pressure. It's Psat. It's a function only of the temperature. Okay. How about this one? This is maybe a little easier. Temperature, if I'm given pressure and quality, the quality is between 0 and 1. It confirms that it's in the two-phase region. It's just saturation temperature, a function of pressure. All right, how about if I'm given specific volume and temperature, and I want to get the quality? V, the given specific volume, minus V sub F at that temperature, divided by V sub G at that temperature, minus V sub F at that temperature. Often we don't write at that temperature, at that temperature, at that temperature. You just know saturated liquid and the saturated vapor specific volumes are functions of temperature. So we didn't write all that subscript right down in here. Now, once I know the quality, let's say somebody said just like up here, I'm giving you temperature and quality. Give me the specific volume. That would be V is equal to V sub F plus quality times V sub G minus V sub F. They all follow a pattern. Just start using the quality, using the other properties. Sometimes, let's say they're given a temperature and specific volume. Often, if you're given another property like specific volume, get the quality first. Then once you have the quality, then use it to get like H is equal to H of F plus the quality, H of G minus H of F. Hey, you know a shortcut? We could just replace that by HFG. Yep, true. It's the heat of vaporization. It's an extra column in the table. If I pump some heat into a substance of mass M, there will result a delta T in change, a temperature. And the constant of proportionality that depends on different substances is specific heat. So heat transfer in causes an increase in temperature. If I have more mass, hey, then I need more heat. It's proportional to mass. And there's a constant. Iron specific heat, water specific heat, lead specific heat, copper, different substances, solids and liquids typically. But in thermo, here's a definition of a specific heat. And here's another definition of a specific heat. So now you get the two specific heats. Specific heat holding some constant, the volume constant, is equal to the rate of change of U with respect to temperature. How would that be used? Well, let's go to first law. The first law for a differential form is du is equal to, let me do cap U here, is equal to del Q minus del W. Differential form of the first law, neglecting kinetic and potential energy changes. If I want to put it on a per unit mass basis, I usually put a lowercase q, lowercase w, lowercase, that's on a per unit mass basis. But this is on a total mass basis. All right, so let's do this. If I want to have a system where the volume is equal to a constant, a small system, and I have this first law apply where I'm having some heat transfer into it, what is the work? 0. Del Q is equal to du, or del cap Q is equal to m du. It's equal to m d, this is a du dt dt, but that was holding volume constant. So it's equal to the amount of heat transfer in is equal to the mass times a property that's defined as du dt holding V constant. There's its definition. Sometimes mathematicians put 3 equal sign with 3 bars in it. Mass, specific heat constant volume, dt. So we see that it lets us relate how much heat is brought in to the temperature change. Let's do it now for a chunk of substance that's at constant pressure. We like piston cylinder. That allows us to have constant pressure. There's our substance right there. Now if I bring in some Q, right, del Q, what can happen to the system? It can lift the weight. So our first law starts in a form like this or like that, but it comes down to del Q is equal to dH, change in enthalpy. Yeah. And so, or the amount of heat transfer in is equal to the mass times dH dt, holding pressure constant, because that's the pressure constant process, dt. What is this defined as? C sub P. So the amount of heat is equal to the mass C sub P dt for a constant pressure process versus a constant temperature. So we have 2 specific heats, specific heat constant pressure, specific heat constant volume. K is a property. It's another property, just like C sub P and C sub V are properties. It's the ratio of specific heats. All right, what you can do is take a look. There's a number of figures in the textbook, and they show you how some of this new property called specific heat, C sub P, specific heat constant pressure, varies for a real substance like water when it's in the vapor state. Notice they plot C sub P here. Here's 1.5, 2, up to 6, 7, 8, and what they have here, temperature going up. So it's hot steam, right? But if you wanted to evaluate the steam at, let's say, 500 degrees and 20 megapascal, you would find that the specific heat constant pressure is right there. It does vary. It's not a constant for superheated steam. Okay, this map is showing us how it varies for superheated steam. It's not a constant. Okay, so when you're in a superheated steam and you have a process where you're putting in some heat and you want to know, you're given a mass, you want to calculate the change in the temperature, this needs to be evaluated. Probably just go get it out of the tables. This is going to be a MDH, right? Just get the change in the enthalpy out of the tables. Don't try to do it there. But if you heat a solid, okay, I was going to spend more time on this, but think about adding 10 kilojoules or 20 kilojoules or 30 kilojoules of heat into the solid. Maybe the solid started at negative 10 degrees C, and maybe it's copper, maybe it's mass of 1 kilogram. And at that mass density, you can find the volume occupied by 1 kilogram of copper is not very big. It's about a tenth of a liter. The volume is about 0.11 liter. That water bottle, hold up the water bottle for me, please. How big is that in liters? Half a liter. So 20% would be about the size of the copper chunk we're thinking about. A kilogram of copper, about that size. So you then heat it up. If you heated it up, the temperature would go, if you just pushed in 10 kilojoules, the temperature would go to 15 degrees C. There'd be a 25 degrees C increase in temperature. Would it melt? No, it's only 15. It started really cold. I pump in another 10. The temperature jumps up to 40, 45 or so. Actually, if you want more precise, I got more precise here. It was a 26 degree temperature rise, and so it ended at 16. Then another 26, it ends at 42. Then another 26, and so it's a straight line. That straight line is 1 over the mass times the specific heat. And so for the 1 kilogram, you can calculate or look up the specific heat for copper is about 0.385 kilojoules per kilogram Kelvin, that's C sub P. Sometimes you'll see a book. They'll say C sub P is equal to, for copper, 0.385 kilojoules per kilogram degree C. How do you convert from one answer to the other answer? How do you get, somebody says, they gave me this one in the book, but I'm working in temperatures in degree C. How do I get it into these units? So that's absolutely right. It's the same answer because this, how do you use it? Q is equal to MC delta T. You never multiply by the absolute temperature. You multiply the change in temperature. And so 1K is equal to 1 degree C. First time you saw that, you said, this is trash. Whoever wrote that's wrong. This is a temperature change. The temperature change of 1 Kelvin is equal to the temperature change of 1 degree C. Oops, I can't write. Is that true or false? True. And so sometimes you'll see specific heat in Kelvin, sometimes degree C. You just have to know. You just have to know, right? That this is the same. You can now do it for a liquid. The liquid, something like oil, it may expand a little bit, but if it stays liquid, let's say your engine starts at -20, cold, cold, cold morning, but operating its way up here. Well, what you find is that it heats up by pumping some heat into it. The temperature goes up, true? There'll be a linear relationship between the amount of heat you put in and the temperature increase. And you can get this to be 1 over the mass specific heat. The specific heat for engine oil is it's about 1.9 kilojoules per kilogram degrees C. But a lot of liquids and solids stay liquids. They stay solids. We're not changing their phase. And if you want to do energy calcs with them, you would go to this table, A19. I am overloaded with tables, Professor. Yeah, I know it. But here it is, selected, not all the liquids and solids in the world, and they're giving you C sub P, rho, and K thermal conductivity, kappa. It's a kappa, all right? So here's some selected solids I truncated. Building materials I truncated. Insulating materials I truncated. Saturated liquids I truncated, okay? So if they stay liquids and you don't have better tables for them, then you can use this table for specific heats. Specific heat, constant pressure. Notice the units, kilojoules per kilogram Kelvin. There's a mass density. Good. Now, somebody says, don't we have tables for water? Yeah, we do. Will this value at 300 Kelvin be consistent for, let's say, the density? Yes. And you can prove it. And if you want to, I leave this as a homework assignment. Take the data out of A19 for water at 300 Kelvin. There's the density. And compare it to the data in table A2 at 300 Kelvins around 27 degrees C. Here is the specific volume of saturated liquid, V sub G, come on, V sub F, is equal to 1 over rho. And you'll see that that's good. They compare well. Things tie together. I'm glad there's not disharmony or disagreement between data and tables. Let's say you don't even have some stuff. You don't have I want to make an approximation. These are very common approximations for liquids which are subcooled. So if you know that you're looking for the specific volume of a liquid, as I change the pressure of a liquid, it doesn't really affect it much. It's incompressible. So you just do this. It's called ignore the pressure. And you say, well, it's approximately the specific volume of the saturated liquid at the temperature of interest. Okay? Check this out. You'll use it a lot. Check this out. You use it a lot. Same here for enthalpy. All right? It's an approximation. Liquids and solids are essentially incompressible. True? So let me do this. If I have a rigid vessel, that's one of a rigid tank, a rigid vessel. That's one of our key words, rigid, such that even if I heat it up from state 1 and I go to state 2, what is the volume at 1 compared to volume at 2? They're equal. When you see the word rigid, put that in, that the volume is not changing. True? All right. Now, somebody says, I want you to calculate how much heat it takes to take so much mass and change its temperature. Oh, if I just knew C, the specific heat. But in thermo, we learned there's a difference between C sub V and C sub P. Which one should I put in here? C sub P or C sub V?
Either.
You're ahead of me. You must have read the book, which is good. If you read the book and you know where I'm going, kind of. But, you know what he said? Either. Why either? And you know the trip hazard that a lot of students will do is they'll say, I just learned the difference between C sub P and C sub V. C sub V, constant volume. Rigid tank, constant volume. Let's search the book from cover to cover and look for C sub V for copper or C sub V for something else, right? And then they'll come to me and they say, hey, I didn't find it. I said, why didn't you use C sub P? Because this is a rigid tank, constant volume. But the thing is when it's incompressible, does the volume change? Regardless if the pressure changes or anything else. So C sub P is equal to C sub V. You can use either. Professor, why did they put C sub P in our table? We just went to that table. What did they put right here? They put C sub P. Why didn't they put another column for C sub V? Because it's the same value. Then why didn't they just drop the subscript? Because, you know, this is the first class where I've ever seen the subscript in the first place. Every time I've seen it, it's just C for liquids and solids. A lot of textbooks drop the subscript. But probably more than half for solids and liquids, they'll put C sub P on it. Okay? Solids and liquids. It's a good approximation. Solids and liquids. Steam, no. Ideal gas, absolutely not. The ratio is about 1.4, about 40% difference. All right. Who remembers the ideal gas equation? Plenty versions. PV is equal to N R bar T. True? This R bar is the universal gas constant. I could put PV is equal to M R T, where M, this R is R bar divided by the molar mass. Did we cover that already? Say yes. Thank you. All right. So there's a difference between R and R bar. Know it. Make sure. There is one table. It's not available to you on exams. It's embedded in Chapter 3, but it's a nice table. And it gives you R, which is simply R bar divided by the molar mass for air, for ammonia, for argon. So the number does change. See that? For both the SI as well as BTU, pounds, and degrees R. R bar is 8.314. Just like that. Ideal gas model. There's three things on the model. 1, 2, and 3. This one, that the internal energy is a function of temperature only. That the enthalpy is a function of temperature only. Okay? That's what they're saying right here. This one we understand, that's our equation, but the model includes the ideal gas equation plus the observation that U is a function of T only and H is a function of T only. How did they ever get that? Let me explain it to you. Joules. Anybody heard the name Joules? Great scientist, did a lot of experiments. They were contributed to the development of science and engineering. Hence, kilojoule, unit of energy in SI. They honor him by putting his name in there. What was Joules' experiment? He took a water bath and he had probably a lid nice and insulated. Very well insulated water bath. Very, very well insulated water bath. And he took and put thermometer in there and he could measure the temperature of the water bath. And inside the water bath he had a big chamber that he could pull a vacuum on, and he had a little valve that he could turn up here, open and close that valve. And he had another big chamber. So he had chamber A and chamber B. All right? And he had a little port where he could hook this to a vacuum pump, and he pulled everything out of chamber B with the valve closed. Everything's pulled out of B with the valve closed. He has another valve, and he hooks it up to a tank. He hooks it up maybe to nitrogen, or he hooks it up to air, or he hooks it up to any other ideal gas, helium. He plays around with this. He hooks it up to a lot of different stuff. And he hooks it up so he can boost the pressure. So he starts this tank A maybe with this ideal gas or that ideal gas or that ideal gas, but they starts at different pressures as well. Maybe he starts at 100 kilopascal. Maybe he starts at 500 kilopascal. Maybe he starts at 1,000 kilopascal. True? Something. He starts at different pressures. Maybe he starts at 10 kilopascal. It's a vacuum. It's low pressure. He lets it all get nice in equilibrium. What's the temperature of the gas in A compared to the temperature of the water in the bath? Equilibrium. He waited a long time. What is the temperature of the gas in tank A after he waited a long time? It's in thermal equilibrium with the water. They're equal temperature. True? Then he opens the valve. He looked very carefully at the temperature of the water after he opened the valve, and the gas from A went, and some of it went into B, and then it became into mechanical equilibrium. True? In A and B, so they're the same pressure. Maybe it went from 500 down to 250 kilopascal for both of them. See that? The pressures in tank A is lower because some of the mass is over in B. But he looked carefully at the temperature of the water. It's well insulated. And guess what the temperature of the water did? Do you think the temperature of the water increased or stayed the same or went down? Did it go up? Did it go down? Or did the temperature of the water stay the same? Okay, let me ask you this question. If there would have been a heat transfer from the gas into the water, would the water temperature go up or down? Up. If there would have been a heat transfer from the water to the gas, would it have gone down? The temperature of water would have gone down. All right. What would motivate a heat transfer either to the water or from the water? A temperature difference is the only thing that can motivate a heat transfer. So, if the gas got cold as it expanded, the water would have gotten colder. True? If the ideal gas in the tank A, as it expanded into B in equilibrium, if it would have gotten warmer, what would have happened to the temperature in the water? It would have gotten warmer too. He made precise measurements, and you can't believe it because he made these experiments, so he didn't know what he would expect, but he found consistently, no matter if it was this ideal gas, this ideal gas, this ideal gas, for modest pressure ranges, meaning you didn't pack it in such that it became a real gas, it still behaved as an ideal gas, that only this happened again and again and again and again. The temperature of the water did not go up. The temperature of the water did not go down. Now you make the observation there was no heat transfer from the gas into the water. So now you make the observation the temperature of the gas didn't change. The pressure changed. So we start with a system that's like this. We end with a system that's like this. See how the system's deformed? The system is only the ideal gas. Write the first law for the ideal gas. U at state 2 minus U at state 1 is equal to how much heat was transferred into the gas during the process minus the work the gas did during the process. Does that make sense? There was no temperature change. There was no heat transfer. Zero. What about work? It expanded into a vacuum. He had to pump a vacuum in that second tank. As it expanded, did it push back? Did it have any resistance as it pushed back? Did it do any work? The boundary work is zero. All right, so what do we conclude? That U2 has to be equal to U1. Let's take a look. The U is a function, U2 is a function, let me write it out this way. U is a function of T2 P2 is equal to U T1 P1. Did the pressure change? Sure did. The temperature change? No. Can the internal energy be a function of pressure? I changed the pressure, but the internal energy has to be the same. It's not a function of pressure. He concluded the internal energy is not a function of pressure. From other experiments, he knows that if he heats it up, it'll increase in temperature like the other ones, T versus Q. So he knows that the internal energy is a function of temperature. But it's not a function of temperature and pressure. It's only a function of temperature. Hence, U is a function of temperature only. That's a long thought experiment. It's Joules' experiment. You can read more about it on the internet. Thank you for your attention.